the main difference today is we move from unitary one-dimensional. These guys are elementary operators. So here's your bracket notation for the actual operator, elementary operator. Nilpotent projector. Okay? So we've got those. It's just they don't come quite as simply as a Sylvester formula or anything like that. We pull this out just directly, Sx plus Isy. Well, look what happens to it. Okay, 1/2 plus I times I half, that cancels. Okay, and then 1 plus I to minus that gives me 1, right? So there's your very obvious raising operator, right? Here's their creation-destruction notation. Okay, those are the combinations that do the job here. And you can see by looking at it this way, it's pretty easy to show what this is. Now this is the guy that's diagonal, but the other guys, this thing right here, form for SC. Okay, that's the creation-destruction form with a little 1/2 and then a -1/2 for that one. Or if you're thinking of spin up and spin down, you write it that way. 1 and 2 is spin up and spin down. Okay, this guy creates an upspin. Okay, from the vacuum. Okay, this guy creates a downspin from the vacuum. Okay, so there's upspin, there's downspin. That's the notation we're going to be using from now on, where we put the principal quantum number here and then the subgroup quantum number here. So this guy right here destroys a downspin and creates an upspin. See, there's the destroyer of the downspin, there's the creator of the upspin. Basically the destroyer of the 2 and the creator of the 1, where we were just numbering them 1 and 2 without any physical embellishment like you do with these spin up and spin downs. Okay, so this one, destroying a down, which is a 1/2, and creating an up, which is a +1/2. So this is a -1/2 that you've destroyed. So now you got a +1/2, and then you pick up another +1/2 from this one. That's a creation of raising by 1 quantum unit. Okay, so that's the story of the raising and lowering operators put in its most elementary operator form. Okay, and this one destroys an upspin, so you've got a -1/2 from that, and then it creates a downspin, which is another -1/2. So that one gives you a -1 unit, destroys angular momentum by 1 unit. Does that make sense?
Yeah.
So it's quite a load here. We put all these different notations on one page, and each one tells you a little bit about it, and another one tells you a little bit more. But this kind of sums it up. So that's the thing I want to get through. Because this is what we're going to do. We're going to be making these as our basis. And it's going to be made of creation-destruction operators to, well, what are these numbers here? This is J plus M, this is J minus M. So I'm going to be replacing the oscillator quantum numbers with sums and differences of the principal quantum number for angular momentum and the secondary subgroup quantum number for the z-axis angular momentum. And then there's sort of backwards right there. J is nu over 2, which is the nu here is n1 minus n2. The m is, let's see if I got that right, and that should be a plus sign. And then this is m is n minus 2. That's a bad error there. Nu is n1 plus n2. Got to change there, it's done right. Okay, so there's the connection between angular momentum calculus and physics and of R3 basically, but also U2. And then the oscillator, spin up, spin down calculus, angular momentum of an oscillator, which is U2 connected to the R3 mathematics. So this is what we're going to be talking about. This is the creation destruction operator that will work. And look what it does. Destroys a 2, creates a 1. Okay. When you destroy the 2, the larger number is n2, because n2 minus 1 is lesser. And then n1 plus 1, we've already looked at this thing right here. Okay. Well, that's going to be an S plus matrix. Okay. So stick n1 plus 1, that's j plus m plus 1, and n2 minus 1, that's j minus m, and you get an m plus 1 right there. So there is, I claim, the shortest derivation of these relationships, which are in quantum mechanics books everywhere, but take 4 pages to derive. Okay. This is really efficient. So that, I think, is what got Schwinger started on making a clean evaluation of these matrices. So there are the matrices again, but now just calculated by that formula right there. And then you go on and do the 3 halves and the j equal 2 tensor, and that's what we got to work on now. Is what's the exponentiation of these operators? What's the actual? These things generate rotations. This is an infinite group, so your basis is not projectors so much, not so much idempotents and nilpotents. Your basis are these generators, which are the derivatives of the actual operators, rotation operators themselves. So that's what we have to do next time to get us all the wave functions that are functions of coordinates. So we're getting there. Make any sense?
Yeah, I have a question.
Sure.
In the previous slide,
Is this a different slide?
yeah, it was one previous one, but I think
We can go there very quickly.
yeah, there.
Right here.
Yeah. So down there in the corner, you have a annihilation operator that destroys the down spin, and you have
It's going to annihilate a down spin.
and it's going to create an up spin.
And it's going to create.
What if the state that you have there, you use like, you put like a up spin? What's gonna happen?
I should be really putting here up spin, and then if we're talking about 2 dimensions, I would have another thing. But this is just the fundamental. Okay. So what this thing does is it just kills this thing and leaves you the vacuum.
And the other one.
And then this one says, "Oh, I don't want to go out of business. I'm gonna put something there. You nasty nihilist. I'm gonna make this."
This one, the one on the right, that one is creating. That one is annihilating the up conversion.
Right.
The up spin. Sorry.
Yeah.
And that one is creating the down.
And this one finally comes in and says, "Hey, I'm going to produce a downer," and that's what he does. Because this has made the vacuum, right?
Mm-hmm.
And then this guy comes and sees a poor vacuum and says, I got to take the vacuum tool down. I'm going to take the vacuum down. So he produces 1 quanta down.
All right. I see. Can you like have like?
It's a little confusing because this is what we were doing before, right?
Mm-hmm.
And the 1s and 2s, you had no, what do they mean? It could be vibration of X and Y, right? It doesn't have to be right and left angular momentum, right? It could be any 2-state system. Some weird ellipse this way, and then the other one some weird ellipse this way, right? And they're called 1 and 2. So this is a more general expression of what the creation and destruction operators can do, and they come in many varieties. Remember, you can take any linear combination of creation and destruction operators and call it your new creation operator, and then the orthogonal complement is your new destruction operator.
Okay, there is something I would like to know. So if I have the annihilation operator acting on the, in the up spin,
Mm-hmm.
would it make sense if I have like a down spin, the annihilation operator doesn't have anything to annihilate. So, and then I have the other creation operator that will act in the down spin.
Well, the thing is,
you see what I mean? I just want to understand the
You're
bookkeeping.
hitting on a very important problem with oscillators, and that is they stop at 0. There's no negative states associated with the harmonic oscillator. Now, where would I ever get negative states associated with a harmonic oscillator? Well, I'd have to build a whole theory with antiparticles or something. But we don't do that. We stop at the bottom. And so when I make a vacuum, then it's understood that any destruction operator that hits the vacuum, any power of any destruction operator that hits the vacuum, right away gives you 0.
Doesn't matter.
Yeah, it gives you a 0 vector.
Does
which means you're out. You've just made nothing that's less than the vacuum. The vacuum, of course, is 0, but just putting a destruction operator on the vacuum, you're out of business.
You know, the way I see it is like if you were a particle and I hold you and I have like, suppose like I quantize my energy, like I have like 3 units of energy to hold you.
Right.
But you have
some sort of internal energy.
Yeah.
Right.
But you have like
oscillator's got external energy.
But you have like 2 units of energy.
Mm-hmm.
I'm holding you, so it will take you 1 more for you, which represents a negative unit for you.
Right.
To move.
And
that's not the way it works, right?
The harmonic oscillators of electromagnetism absolutely do not work that way.
But you see my logic, right?
Yeah.
I mean, it's logical.
It would be nice if you could have sort of a bank that would keep track of the internal, some sort of internal, and this is just external stuff.
So nature does not do that.
Oscillator theory doesn't have that. Maybe it should. Maybe it should rebuild the whole thing with something like that in it. But I see no reason at this point. Now maybe this would help with Mr. What's his name's Twister, Penrose, right? Mr. Penrose's Twister. Maybe those things could use a conjugate space to go with the ordinary oscillator space. But in ordinary quantum field theory, it doesn't have it. And in the quantum field theory we do for lasers, doesn't have it. And you're talking about one-dimensional oscillator at this point. Now here, we got 2 dimensions to play with. So when I come with a destruction operator to destroy a spin up, and the state doesn't have any spin up, it's already vacuum and spin up, I get 0. And that's the whole reason for having the normal ordering, remember? Putting those destructors to the right. Okay? Because now when I apply a vacuum here, they all give 0, 0, 0, 0. And this thing I've calculated, which doesn't have them sitting on the right, is giving me some non-zero states. But I do absolutely need, for doing this formalism, the ability to just say, I get nothing. Not the vacuum, I get nothing. It's 0. I'm ignoring that term.
I'm very puzzled by that idea.
It is. Yeah, no, it's a major worry, because most of the time we're used to space that goes in both directions. But we don't have that here. When I get to the vacuum, I don't go below that.
Probably won't sleep tonight.
So we're thinking about, well, how would you do otherwise and still get all the stuff we need, right? That's a catch. Yeah.
I've seen this applied fairly recently for SU3 problems, where you start off with the weight diagram exactly the same way, and you start at a corner, and you basically walk yourself
There's no
across.
operator to take you away, you know, outside of that corner. Yeah.
Right,
And that's
you
going
go
to be true for
zero.
all the unitary groups. There's a floor. Can't go below the floor. And there's a floor in all of the different dimensions, right?
So you usually start on the periphery
Yeah.
and work your way across. You have a methodology for doing it, but the process
Now,
is the same.
there are weird spaces like the Banach space, which are continuous, right?
Or you can do whatever you want there.
Yeah. It seems that way. Yeah.
Depending upon your work.
And that's the trouble with a continuous formalism, is it's really hard to get on the computer, because now you have to coarse grain it. You have to make it discrete. Because you don't have a continuous memory. Right? It doesn't exist.
Hard to address.
Yeah. Yeah, continuous address, right?
Yeah.
It wouldn't be a digital computer anymore. It'd be a continuum computer.
Damn.
Yeah. Now, analog computers are that way, but an analog computer has noise.
Yeah.
It's a real physical, living thing, you see, and your numerical accuracy is determined by temperature.
Yeah, when the transistors do not.
Yeah, exactly. Anything else embarrassing or not embarrassing? Okay.
We
Well,
may have
fun
clipped
with
this.
the next part.
I noticed an issue here. This video may be clipped, so you might need to go to the previous year to get the full content.
The next, the 24, which I've already pretty well set up. The thing that 24 doesn't have is a good linking list. The linking lists are all 2015. So we got to bring those up to date, but it seemed like everything else was in pretty good shape. And then we need some links for